Hey ladies and gentlemen, welcome back to another Try in Science. We're going to do a little energy review, so grab your energy review packet and join me for a quick review to help you get ready for your energy test. All right, let's look at our test coming up next class on E-Doctrina. First of all, we want to summarize energy. So find a place to write and let's figure out if you can summarize what energy means to you.
What do we mean when we talk about the energy in a candy bar? Or conserving energy? Or finding alternative energy sources? What exactly is energy? Energy is a property used to describe a wide variety of things, from the tiniest particles to the most complex systems. But unlike physical properties, such as color, length, or temperature, it's better understood by what it can do than how it looks or feels. The standard definition of energy is the ability to do work. In other words, it's the ability to create some sort of change in an object, whether it's the object's location or the motion of its atoms. All objects store energy, but they differ in the amount and forms of energy they carry. For example, chemical energy is stored in the bonds that hold molecules together. Potential energy can be stored in an object's position, like this apple hanging from a tree. And when the apple falls to the ground, that potential is transformed into kinetic energy, or the energy of motion. Not only does energy come in many forms, but we can also convert it from one form to another. For example, we make use of the chemical energy stored in fuels like oil and coal by burning them. When we do so, we convert their chemical energy into thermal energy, or heat, to warm our homes. Or we can use fuels to produce electricity, the energy carried by electrons moving through a wire. So if we can convert energy from one form to another, why are people so concerned about conserving it? The fact is, not all energy forms are equally useful, and not all conversions are easy to do or equally efficient. Take electrical energy, for example. We use it to power all kinds of technological devices. However, as the electricity drives computer processors and lights up TV screens, it's transformed into other, less useful forms of energy, especially heat and light. That energy isn't lost, it still exists, but once released into the surrounding environment, this relatively small amount of heat and light can't be recaptured and converted back into electrical energy. And so, whether it's fossil fuels today or large-scale alternatives in the future, we'll continue to need new energy sources if we want to keep our high-tech, electrified world running.
How'd you do on your summation of energy? Pretty easy. We're going to talk a little bit more about energy, so have your review packet handy and let's review the types and forms of transformations of energy and thermal. Alright guys, I'm in my review packet and I'm enjoying the review because I'm going to help myself on my test. Let's start with something we did quite a bit ago when we talked about solids, liquids, and gases. Comparatively, temperatures. Think about what's happening to the molecules of the solids compared to the molecules of the liquids and the gases of the same type of material, for example, water. The spacing of the molecules and the energy. All right, pause, figure it out, fill in your chart, and move on to page number 2. Now we're going to talk about some heat transfers. There's 3 main ways that heat can be transferred. Conduction. Heat's transferred through touch, whether it's touching of the molecules within an object or one object to another, like when you touch a hot pan, the heat is transferred to your hand. It happens best through solid objects where molecules are close together. Think about a bowling ball knocking down bowling pins. If the bowling pins are close together, you're more likely to knock down another bowling pin and get a strike. But if the bowling pins are far apart, it's less likely for them to conduct or transfer that energy. Molecules and solids are definitely closer than liquids and gases. Radiation doesn't need any molecules at all. It's the movement of energy through electromagnetic waves can happen through empty space. A great example could be the sun, transmitting its energy from the sun to us, 93 million miles away. And finally, what's left? Well, air and liquid can be considered fluids. Transfer of heat through a fluid can create a current. As one air or liquid molecule moves, it has a slight attraction to its neighbors and pulls them along with it. And that's how you get wind. Uneven heating of the Earth's surface causes air to move and rise, and it pulls its neighbors along, creating a breeze. Calories. Calories are a way to measure thermal energy. It's typically measured by 1 gram of water being heated by 1 degree Celsius. A gram of water is a 1 centimeter cubed amount of water. So by that definition, how many calories of heat energy, thermal energy, would it take to heat 1 gram of water from 10 to 80 degrees? So we're going up 70 degrees, therefore 70 calories. 70 degrees for 1 gram of water. Now we're going to have 10 grams of water. So everything we figure out will be multiplied by 10. The temperature is going up 30 degrees times 10 grams is 300 calories of energy. See if you got this one right. We're moving 10 degrees for 100 grams. That's 1,000 calories, which is a kilocalorie, which is actually how the energy in food is measured. So 1 calorie of something like, let's say, a calorie in a donut is actually 1,000 of this type of calorie. So the way scientists measure this is they'll take that object, that food, they'll dry it out, grind it up, and they'll actually burn it in a special machine that can measure the amount of temperature that rises in a liter of water. Okay, every time that liter of water rises 1 degree, that's a kilocalorie, which is our food calorie. Okay, so 300 calories is quite a bit of energy if you think about how much the increase of the temperature could be. And speaking of temperature, let's take a look at this example. We've got 2 different pots of boiling water. Using the chart, let's see if we can fill in the details. Small and large pot are both 100 degrees. You know why? They're both boiling. Boiling water always boils at 100. Pure water cannot be hotter or cooler than 100 degrees Celsius when it's boiling. Now there's less molecules in the small container than the large. The molecules are both going fast. In fact, probably going about the same speed because they're at the same temperature. But what's going on with the heat energy or thermal energy? Well, there's less molecules in a small pot compared to the large, therefore there's less energy. That was similar when we talked about a frozen pond having actually more thermal energy than a campfire because the frozen pond has so many more molecules. All right, insulators, materials that don't conduct heat. Foam, cloth, glass, or air are all definitions of materials that will block the transfer of thermal energy through touch. So we use insulators when we grab the handle of these hot pans because we don't want to get a burn. All right, let's check out the 6 types of energy that we learned in our notes. We've talked about light, sometimes called electromagnetic or radiant energy. Light can be visible or in forms of energy we can't see, like microwaves, X-rays, radio waves, and gamma rays. These are the electromagnetic spectrum. Some of them have low energies and some high, but in either case, they can radiate through space without molecules needed. Chemical energy is the energy stored in bonds between atoms, such as when you combine sodium and chlorine and you get a reaction that releases energy. Sometimes you get energy, such as in a fire. If you add enough heat, you can break the bonds between carbon atoms and release energy. Similar thing happens in your cells as you release the bonds in sugar molecules. Thermal energy is kinetic. It's a motion, but we're talking about the motion of the molecules inside of an object. Gas molecules have more thermal energy than solid molecules of the same material. Electrical energy is another form of kinetic energy, but we're talking about a specific motion. It's the motion of an electrical charge. Remember, batteries have positive and negative terminals for the motion or flow of electrons. Nuclear energy is the nucleus energy in an atom. So we're not talking about the bonds that can happen when you do a simple reaction, but we're talking about the energy that's holding the protons and neutrons together in an atom. And that can be released in 2 ways. Fission is when you break a large atom apart into 2 smaller atoms and likewise release a lot of energy, such as in plutonium or uranium. Fusion happens on the sun, where you take smaller atoms like helium and hydrogen and fuse them. A small amount of mass is lost when this happens, and that mass is converted directly into energy. Mechanical energy is a motion of moving material. We have our kinetic energy of motion, but also potential. because an object can be in a position or a location that it could move. So objects that are higher up have more potential to fall, being affected by gravity. As they fall, their potential energy converts to kinetic energy of motion. And finally, sound, which is again kinetic energy, but since it's a special sense that humans have and talk about, we talk about the vibrations of sound waves. They need to move through a material that doesn't work in empty space. Like a drum, the vibrations move the air molecules which eventually reach your ears. So make sure you know all your types of energy. Notice there's some things you might think are missing, like solar energy. That's just a coined term that is meaning the generation of electricity from light from the sun. Therefore, the solar. But it's not really included in our. We also don't use wind energy or thermal. Hydroelectric. Those are ways to make electricity with different conservations. Speaking of conservations, energy cannot be destroyed or created. It just changes form, or we say it transforms. Here's some examples. Nuclear energy in the sun creates light energy and can hit a plant, causing photosynthesis. It's a chemical reaction, creating sugar. Electrical energy can convert or be transformed into sound energy in a radio. Chemical energy in food or in a battery can turn or move something, such as the motion of an object. Okay, let's compare renewable to non-renewable, starting with definitions and examples. Positives and drawbacks. How'd you do? Do you have any different examples? Maybe at some point, the pros for renewable energy will outweigh the cons, and maybe there will be a tipping point and people will start to use a lot more renewable energy sources. All right, here's our pendulum swinging. Maybe it's a bowling ball on a rope. As it's at its highest position, it has its greatest potential energy if you release it. That potential turns to kinetic. The motion continues until it reaches the next high point where it would turn around, stop, turn around, and begin its trek back. Okay. Why doesn't it continually always reach the highest point on the other side? Well, there's some friction, there's some air resistance, and a little friction at this point here. So the pendulum cannot get higher than the position at which you release it. And eventually we might stop due to energy lost. And by lost, I mean converted into other forms of energy, such as heat by the friction of hitting the air molecules or this rubbing action here. All right, let's talk about reflection and refraction. Energy can be reflected or refracted, which means bent. So let's use light as an example. Light can travel at the speed of light, but only in outer space. As it enters our Earth's atmosphere or water or glass, it actually changes its speed, which causes a slight bending of the wave. And it can change this angle, which can also change how you perceive it, making things look different to your eye than they really are. This pole is actually straight, but it looks bent as it enters the water. This is how eyeglasses work. And let's review as a little end up here. Let's talk about energy.
As you probably know by now, we've been working with...
As you watch, keep in mind the question we're asking is, what is energy, and what do you think about it?
There's science questions asked on the internet, and I gotta hand it to you because there are few questions that are as confounding and complex and fascinating and inspiring as this one that the collective consciousness has spewed forth. What is energy? I'm Hank Green, and this is the world's most asked questions. Energy is everything. It's everywhere. It's one of the true constants of the universe, because as long as there's been a universe, there's been energy. And while it comes in lots of different forms that can seem different to us, they all amount to the same thing. Energy is the ability to do work. And work is just the act of displacing something by applying force. So say you stomp on a stomp rocket. The force of your foot hitting the pedal is turned into the force of the air leaving the cannon, sending your rocket sailing. Or maybe you're enjoying a nice patty melt. The energy from that food is broken down for all of the quadrillions of cells that you have to do all of the things that they have to do. Make copies of your DNA, assemble and repair proteins, transport materials from one place to another, make muscle cells contract. You know, all the stuff of being alive. That rocket sailing, your cells toiling away, your phone or computer being on right now to watch me, that's all work being done. And the ability to do these things is inherent in everything around you, even things that look inert, completely lacking in energy, like this log. This log, for example, is chock full of chemical energy because it's made up of combinations of carbon and hydrogen and oxygen formed into lignin, which is the stuff that makes up wood. All of the bonds between all of those atoms and every molecule of lignin contain energy. How do I know? Because if I were to apply enough extra energy, like as heat, to break those bonds, it would release that chemical energy as fire. That chemical energy is also the kind of energy you get from your patty melt. Your body is fueled by the chemical bond energy in sugars and fats and proteins. But this log also contains nuclear energy. Each atom in this wood has a nucleus made of protons and neutrons, and the energy that binds them together is one of the most powerful sources of energy in the universe. If you could split one of the atoms of carbon or hydrogen in this log and rip those protons and neutrons apart, it would release some of that energy. There's so much nuclear energy in each atom that if I could unleash all of it that's in this log, there would be a giant smoldering crater where I'm standing, and everyone in the town of Missoula, Montana would be dead. So everything that's made of atoms has nuclear energy locked up in it. But also, it turns out that mass and energy are the same thing. You might have heard of this little equation that a German patent clerk came up with about 100 years ago. E equals mc squared. And there are so many other kinds of energy that I'd love to get into if we had the time, but even though they may seem different, they can all be used to do work. Whether it's driving a turbine, or moving an engine piston, or allowing the screen on your tablet to glow, or if it's that most mysterious of energies, dark energy, causing the universe to expand more than it seems like it should. But here's the thing to remember. Once the work is done, the energy isn't done. Because energy never goes away. It can never be destroyed, and in the same way, it can never be created. It can only be transferred from one source to another, like how the energy in the plants and animals that were in the patty melt were transferred into you. Or it can be transferred from one form into another, like the chemical energy in the wood being transferred to light and heat as fire. You could think of the universe as a constant flow of energy, and we are just little pit stops along the way. Everything your body is doing right now, whether it's your lungs absorbing oxygen, your heart pumping blood, your brain cells firing as you watch me and learn things, all those things are using recycled energy that's been around since the origin of the universe. And simply by being alive, you're releasing that energy back into the environment around you to be used by other things in other ways. So Internet, to answer your question, energy is everything. And for those of you who answered our questions on our SciShow survey, where you feel like you get your energy may be keeping you up at night. Survey takers who have a hard time falling asleep nearly every night get their energy from knowledge first.
All right, ladies and gentlemen, thanks so much for joining. Hopefully that review helped you prepare for your test. Do your best job as you can, of course. Make sure you study. And thanks for trying science. Hey, we'll see you on the next one. Bye for now.